Today, I'm going to talk about our nearest star, the sun, and its variability. And the sun varies with time. And what is its impact on our life here if sun varies abruptly? That is what the discussion point today. So I'm Dipankar Banerjee from Aryabhatta Research Institute of Observational Sciences. Our head office is at Nainital, and you see the beautiful campus of Aryabhatta Institute at Manora Peak. We have our offices and the labs and our temples. That means our observatory telescopes. And our main important elements are the students. So we all live in this campus here at Manora Peak. And we have a new site where we are hosting India's largest optical telescope, namely the Devasthal Optical Telescope. This is situated in a place called Devasthal. So Devasthal also means the place where Devta lives, and that's our temple here. What you see is the Devasthal Optical Telescope. So most of our activities in today, in terms of night sky observations, are happening from this particular site. Today, I'm going to talk about our nearest star, the sun. That is not now observed from Devasthal yet, but what we are doing is we are trying to, combine this observation from the sun from different platforms, namely the ground-based platforms and the space-based platform. And I will also highlight the importance of multi-wavelength observations of astrophysical resources, namely the sun is today's subject matter. So here what you see is that if I look at the sun with the optical wavelengths only, with an optical telescope from the ground station, then we will be able to see this flat, slightly boring picture. On the top of that, we do see sometimes, this kind of dark spots. They are called sunspots. They are locations where strong magnetic field is emanating from underneath the sun. But interestingly, if I look at the same object with other wavelengths, suppose I look at with the infrared camera from a slightly high altitude mountainside, because in the high altitude mountainside, we still, the longer wavelengths do penetrate. And as you see from the top panel here, this is the the electromagnetic spectrum. And as you know, that this part can travel through our atmosphere and we can observe, but shorter wavelengths, if you want to observe, you have to go to space platforms. And if we are going to space, then through a UV telescope, if you look, the sun looks really very exciting. So we do see many features. We see locations where sun is very bright, and now we understand that these are locations where there are presence of strong magnetic field. And just because of the presence of the magnetic field, a lot of plasma is confined in these regions, and that emits, in all different wavelengths. And even if you go to higher up in the atmosphere of the sun and look at it at even shorter wavelengths, namely the X-rays, we see, again, those active regions which produces a lot of X-rays. We also see dark regions. These are called coronal holes. This is the image of the corona as taken from X-ray telescope from space. So generally, these bright regions are called active regions, and these not so bright surrounding regions are called the quiet region. But we will see later on that nothing is quiet really in the sun. So there are observations of variability of different time scales in the sun. So here you see a movie from Solar Dynamic Observatory, which is looking at again in a higher atmosphere of the sun, and you see the same active region here, which is hosting lots of magnetic field, and they are formed in the form of these kind of closed structures. These are called coronal loops, but sometimes these coronal loops will become unstable, and when they become unstable, they may explode. And when they explode, whatever material is confined within this kind of closed loop system will be ejected into the interplanetary space. So now you will see that this interplanetary space, I mean, this ejecta will travel into the interplanetary medium, and it can reach Earth, and it can have interactions with Earth. So here you see again a repetition of the same ejecta. Some amount of material is thrown out. Some will go back to the surface of the sun and also will hit, and will have lots of dynamics here as well. So all these phenomena also allows us to look at the properties of these materials. So this also provides us the ideal laboratory for plasma physics. We want to understand what kind of compositions are there, how do they change. So that provides a beautiful laboratory for atomic physics, particle physics, nuclear physics, because there are thermonuclear reactions are happening right into the core of the sun, which I'm not going to talk about too much here. But I just want to highlight that it's just one object, sun. It provides you a laboratory for studying various branches of physics. So those who are interested in physics as a subject, applications are many just for the study of the sun alone. Here I show again a movie taken in multi-wavelength. This is the white light image, which shows that these kind of strong active regions having many sunspots. What you see is these dark regions. They're called sunspots. And as sun is rotating from west to east side, you see these kind of magnetic loop system. Some of them are facing towards us. And this is taken from a coronal imaging, 171 angstrom image from Solar Dynamic Observatory. This is taken from a 304 angstrom passband image. These color images represents different temperature plasma, different layers of the atmosphere of the sun. So this is representing a temperature of tens of thousands of Kelvin, situated at say about 1200 kilometer above the surface of the sun. This is representing about a 0.8 million K plasma, which is for regions which is beyond 2000 kilometers from the surface of the sun. And this is the surface of the sun. So what it can very clearly see that everything is linked somehow. So the location of the same magnetic regions on the surface of the sun, which are the sunspots, are connected by these magnetic structures, and they are all the way linked between these different layers of the atmosphere of the sun. So it is again important to do multi-wavelength study for a complete understanding. Now, if I leave the sun and go into the interplanetary space, here is a movie taken from different satellites, because one satellite cannot have so many different instruments covering all these sun to earth distance here. So if I now take a slice, this is what is happening at the edge of the sun. And then, this ejecta has come out, and we are taking it from these things that are called coronagraph. So this ejecta was recorded by the coronagraph, and then, one layer of this outer coronagraph. Then we have another instrument called heliospheric imager. This is inner heliosphere, and then this is the near Earth environment. So you see the other planets also within this field of view. So basically what it shows is that we need multiple instruments, sometimes multiple satellites, to look at these sun to earth distances and continuously monitor it. If you really want to do a study, this is a field called space weather. That means there are certain these dynamic explosions happening on the sun, which are called the solar storms. If they happen here, they will travel through all the way to the interplanetary space and eventually reach us. So to monitor this, you need a continuous view of this different layers as well. So that was active region and related to the big sunspots and so on. But I just mentioned that there are regions in the sun which are so-called quiet. But this proves that nothing is quiet. This, again, taking different slices through the different atmosphere of the sun, this represents the magnetic field evolution at the surface of the sun to a region somewhere in the disk center which appeared to be dark and quiet. There were not very big thing happening. But now if I look at through a high resolution telescope, these three layers have been observed from a ground-based telescope, because from the ground you can build much bigger telescope. You can't have a 2 meter sized or 4 meter sized big telescope in the space. So the combination of a ground-based observations and a space-based observation is giving rise to new discoveries. Here, what we are studying is again the strong presence of very, very tiny little magnetic field. And these magnetic fields are depicted by two different colors here. The blue represents one polarity and the red represents another polarity. And as you can see that whenever these blue guys are coming closer to the red guys, they will eat each other. And whenever they cancel each other, then you will see this kind of ejecta. These are called solar tiny jets or spicules, which is observed in the chromosphere by, again, a ground-based telescope with H-alpha observations. And then you see the results of these jets in the higher atmosphere in the corona, and you see these kind of brightening, which shows the presence of strong heating. So that explains why the corona is much, much hotter as compared to the surface of the sun. So this is, again, a showcase of combined data from Big Bear Solar Observatory at USA and the Solar Observatory at NASA. And these jet-like structures are also called spicules, as I indicated here. And I want to also highlight that these kind of work is happening with really multi-institutional, multinational collaborations, which is very much important for a discovery quality science now. Now, I mentioned about the corona, but when we look at the coronal images, mostly during the total solar eclipse, I guess some of you have the experience of seeing the total solar eclipse. When does a total solar eclipse happens? When the moon comes between us and the sun. So thankfully, during the total solar eclipse, and if you are in that lucky position, in the sense, a position which is called umbra, where the solar disk is perfectly covering the solar disk. What happens is, normally, the emission which comes from the outer atmosphere of the sun is 1/1,000,000th time fainter as compared to the light which comes from the disk. So, unless I block the solar disk perfectly, I will not be able to see the faint emission, which is 1/1,000,000th time the intensity of the brightness of the solar disk intensity. I will not be able to see the corona. Now, this is total solar eclipse images taken in 2006, 2008, 2009, 2010. There are two information which I want to convey through this slide. One is that you can artificially create a total solar eclipse kind of situation in a satellite platform. These are called coronagraphic instruments, and we are building such a coronagraph to mimic the total solar eclipse situation and study the corona continuously rather than waiting for a total solar eclipse to happen. The other interesting element which I want to highlight here is these images are actually superposition of two images taken, one with the red line and the other one is the green line. So the red and green line actually corresponds to two different ionization state of iron. When I say higher ionization state, namely this particular line, 5303, green line, that represents a coronal temperature which is slightly higher than the 11. Because when we go on heating any ion, then you knock out more number of electrons from the outer layers. So that's how you get the ionization states of different elements. So here, by comparing these two ionization states, we can get an estimate about the temperature in the corona. So here, interestingly, what it is showing is that the red plasma and the green plasma is not always superposed. That means solar corona is highly multi-thermal. Interestingly, there is another little story. The virus corona has been named from solar coronal images. Do you seem to sort of somehow identify this image from the coronavirus? Essentially, the history is like this. The coronal images taken during solar eclipse mimics or resemblance the coronavirus. That's how the name came from corona. Unfortunately, it has not been very pleasant for us, but and solar corona has no responsibility for the generation of the coronavirus, but the name has actually come from the solar coronal image. This is a nice, interesting story. So here you can see that the corona also varies with time. Namely, when you look at 2006 coronal image, when you move to 2008 and 2009 and 2010, you see the structures have evolved enormously. You have many more coronal structures because during 2006, actually, we were having a solar minimum condition. That means sun was not magnetically so active during this period. Whereas in 2010, sun has become differently active, and you had more, magnetic structures, and then you see these kind of changes. So to understand these, structures, we also need to understand what is the global magnetic field structure of the corona on large scale, and how does this magnetic field change on a global scale with different time scales. Because this particular lecture, I'm going to focus on variability of the sun, and now we understand the variability of the sun is completely dictated by the variability of the magnetic field structure in shorter time scales, in shorter spatial scale, and also larger time scales and larger time scales. So the physics is somewhat different, but this slide is showing you that since still we do not have a regular magnetic field measurements in the sun in the outer atmosphere, we are heavily dependent on the theoretical models. So here, this is a combined, observations in the outer layer of the sun, and these are theoretical models how the magnetic field are probably like, because we do not have a direct observation. So what it appears is that the theoretical models of the magnetic field evolution or the large scale field seems to be doing reasonably well. This is a work which has been done at CESI, Kolkata. This is a center in IISER, Kolkata, and one of my colleagues, Professor Nandi, in his group, they are doing this modeling to be able to predict how sun will behave tomorrow, for example. Because if there is going to be a solar storm or not tomorrow will have some implications, our assets in the space, the satellites, and also the near Earth environment can get affected because of the presence of the solar storm. So we need to understand the origin of these solar storms. So we need to understand how the global field is and how the global field is changing. So that's the context. So for that reason, we are having our own mission. It is called the Aditya L1 mission, India's space mission to study the sun. It is a multi-institutional mission. There are different institutions across the country are responsible for building these instruments. But I must be also mentioning that this is a complete Make in India project. What it means is all the payload, all the instruments are indigenously being done in Indian institutions. So it doesn't have any foreign component in terms of the complete build. Of course, having said that, we do use electronic components or computer components from all over the globe, but the instruments and the payloads, what we call, are all built within India. So that way, it is a complete indigenous Indian mission on Indian space platform with Indian satellite. So it's a 100% Indian mission. So as I was telling you the story of the sunspots, how the sunspots are magnetic structures, they emerge from the beneath the surface. The white lines represent the magnetic field lines. They are mathematical visualizations of the magnetic field. And when the lines tangle and break apart, they create these solar storms. So here you see when these magnetic fields are forced to interact with each other, you had this interaction and there was ejecta which went out. So it is important to understand how these sunspots are formed, why they're actually forming at certain time and not are there at certain other instances. And when these sunspots come, how they evolve with time, their time variability, and then these are the short time variable changes you see here because of certain tangling and certain instabilities. Here is a magnetic reconnection and this ejecta goes out. That's the solar storm. And now we have to follow the solar storm all the way to Earth. So that's the task. Now, to understand this, do we go back and look at the historical data? What this plot is showing you, the number of sunspots as recorded in last 400 years. The telescope was discovered about 400 years by Newton, and then Galileo used a Newtonian telescope and so on. But there were scientists in other parts of the globe, and a lot from China. They looked at sunspots very, very methodically, not directly looking at the sun through telescope, but projecting the solar image on a white sheet of paper and counting these black little dots which I have shown you earlier. These are called sunspots, and they counted this sunspot number on a daily basis. And if we now record all these 400 years of sunspot numbers, what we see here, there is a periodic variation. So there are alternative peaks in the solar activity. This is called the maxima, followed by quiet periods, which is called the minima. During the minimum period, you will have very few sunspots, if any at all. And you know what? That this was first observed by Samuel Swabe. He was a scientist who only observed for the period from this to vertical line, only for this kind of number of 30 odd years. And so he has only this amount of data, but already he realized that there is something periodic about this sunspot number. And that's how the name often called solar cycle also on Samuel Swabe. It's called Swabe cycle. So the time variation is predominantly cyclic with a mean period of about 11 years. But there are lots of variations. You see the amplitudes are often very, very different. That means there could be, some solar cycle which is much more, dynamic or much higher scale as compared to the other one. In fact, last 100 years of data which we have, I will be talking about it in my next slide. And during that period, during the 1957 or so, we had a really, really high solar dynamic activity, and there were lots of, solar storms and so on during this period. Now, I will just advertise that this is a unique source what we have within our country, namely the Kodaikanal Solar Observatory, which has been looking at the sun. Of course, this was built by the Britishers. Famous discoveries on the solar, sunspot observations was done by John Evershed and several other British scientists. But after the independence, these institute has been handed over to Department of Science and Technology, and I have been involved with this observatory for last 30 years. What we have done recently, we have now digitized all these images. I'm showing you one example of 1st January 1958, sun observed in multiple different wavelengths. This is white light, which is looking at photosphere, and we call it calcium K. This is about 1,000 kilometers in the atmosphere of the sun. And this is again another filter called H alpha, which looks at about 1,200 to 1,300 kilometers on the surface of the sun. We do have a multi-wavelength data for last 100 years. And this is, I'm very proud of this, archive now, because that gives us a unique source to look at the history of the sun, at least for the last 100 years, with the highest quality images which is available. So we have these databases completely digitized. We have data over 100 years, and digitization was completed, and then this data is available. We have published rather many articles on this, and now this data is heavily used by all over the world, and I'm not part of many of such publications. People have always this kind of impression that the data stays with the observatory or these people, but today we are moving into a phase where data and open data is a very, very important thing for maximum utilization of the data. So this is again a classical example. This is a work which my former student, who is now in Max Planck in Germany, with these collaborations, we have now reproduced the solar cycle, and we also produce this butterfly diagram. This actually gives you the information about the appearance of the sunspot at different locations on the surface of the sun. We call it latitude. So what is plotted here is latitude versus time. So here you see at the beginning of the solar cycle, the sunspot appear to the higher latitude, and then with the progress of the solar cycle, they move to the lower latitude. So there are a lot of physics actually involved. This is completely explained by a theory called dynamo theory. And also what is depicted here is different colors represent different sizes of the sunspots. The bigger, the blue ones are the smallest sizes, and the red ones are the big sizes. So what it also proves here that the big guys are always very close to the equator, whereas the small guys are often to all latitudes, but primarily to the higher latitude as well. So there are a lot of physics actually involved in terms of explaining why there are differences between big sunspots and small sunspots and so on. So some of us work on this, and we have reproduced this composite solar cycle for combining the data across 14 different observatories across the globe. So when Sudeep was my PhD students, we worked heavily on the Kodaikanal data, and when we moved into Max Planck, they had the resources from all over the world, and we cross-calibrated the data across all different digitized archive, and he produced these composites. So these are called composite images. This is going to be the state of the calibration of sunspot area series. So my last slide, that I think the future of solar physics in India is very bright, because we do have historical data, we have our own satellite coming up, and the thing lies with the next generation. We do conduct summer schools. So this is a picture of the attendees of students who appeared in a summer school in 2019 in Leh. So that was the last really big meeting we could do before the corona attack. And this is my group of students who are all engaged in this kind of research. So I hope that with the next generation we'll be able to discover more mysteries of the sun. Thank you.